The forces that curve spacetime in Einstein's universe could also describe the invisible geometry of financial markets, where trades ripple like gravitational waves. And volatility doesn't just spike, it bends the fabric that prices move through. And instead of randomness, we have geodesics, paths that assets follow, not because of news or emotion, but because the market structure itself is warped. And yes, it's speculative. But so was quantum mechanics until people invented financial use cases for it. Of course, this is not rigorous. It's not a formal financial model, yet. It's more like the product of my shower thoughts, daydreaming during my general relativity professor's third chalkboard of writing out the full Kerr metric and conversations with AI. There's no empirical evidence tying market price dynamics to general relativity, but that's what makes it worth exploring. Physics models have inspired finance before: Brownian motion, diffusion in thermodynamics, the Fokker-Planck equation, the Feynman-Koch theorem. So why not general relativity? Even if this toy model doesn't produce alpha directly, it might introduce new ways to think about volatility, time, and liquidity as geometry. We begin by modeling the market as a four-dimensional manifold, smooth and continuous, with time and asset prices as its coordinates. And at every point in this space, we define a metric tensor, a mathematical object that encodes how price moves depend on local structure, things like liquidity, volatility, and systemic pressure, all packed into a single geometric rulebook, the tensor, G sub mu nu, defining the shape of the market's geometry. In this geometry, the motion of prices isn't random. It follows geodesics, the natural paths through curved space, described by the geodesic equation, where the second derivative of price with respect to information time, tau, is offset by the geometry's Christoffel symbols. Those encode how the metric changes. And when no arbitrage exists, price evolution flows along these minimal curvature paths. Just as light follows the curvature of space, prices follow the structure of financial stress. But what causes that curvature? In Einstein's theory, it's energy and momentum. In our market model, it's encoded in a stress-energy tensor. Capital flows, order book imbalances, and volatility all act like financial mass, warping the geometry. And through the Einstein field equation, we equate this deformation with the curvature of the market space. The Ricci tensor tells us how local price acceleration arises, and the scalar curvature compresses that into a single number, capturing how warped the entire space has become. So what's inside that stress-energy tensor? First, volatility squared, acting as a kind of energy density, then a velocity vector for capital or information, and finally, pressure, coming from transaction volume and the imbalance between bids and asks. And together, this structure describes the invisible forces warping our market geometry, forces that evolve continuously, yet ripple out like disturbances in space-time. In general relativity, singularities form where curvature becomes infinite. And in our speculative financial geometry, similar singularities emerge when volatility spikes uncontrollably, liquidity collapses, and systemic pressure creates an inward spiral, a gravitational-like pull in market space. And to track these collapse points, we use the Kretschmann scalar, capital K, a contraction of the full Riemann curvature tensor, capturing how sharply the geometry bends in all directions at once. And when K becomes large, we're no longer in a normal market. We're nearing the event horizon of a crash. Now, if we flatten the geometry, if we assume no curvature, no warping, then the geodesic equation simplifies, becoming a straight line, and in that limit, we recover the classical models of finance, specifically geometric Brownian motion, and the Black-Scholes equation, where price follows a stochastic path with drift mu and volatility sigma. And this shows that our curved geometry isn't a rejection of standard theory. It's a generalization, a deeper layer beneath the flat assumptions. To actually implement this model, one could start by computing the stress-energy tensor from high-frequency data, extracting volatility and liquidity metrics across time, then invert Einstein's equations numerically to solve for the market's metric, the G sub mu nu, then simulate geodesics, tracing likely price trajectories, and monitor curvature invariants like K to detect instability. And even if this is speculative, exploring structure in markets through differential geometry might reveal patterns that standard models leave invisible. This speculative model isn't financial advice, but an invitation to think differently. Could markets have geometry? Could they have hidden structure akin to gravitational fields? If you're curious, join the exploration. I'm Joel. Subscribe for more speculative ideas at the intersection of physics, finance, and other mathematical topics.